Right. So the last two videos were on image enhancements in the spatial domain. Okay. And so let's try to quickly go through them. And if you have any questions, please stop me wherever you want. Okay. Because this would be the last class. So particularly for those who are from MTech and also maybe some MS and PhD students, this content some of this content was there earlier in computer vision for the particularly for spatial filtering. So there will be some amount of repetition you would see here, but to keep it self-contained, and also for those of you who are doing image processing related course for the first time, I allowed that repetition. Okay, let it be there, I thought, so that this will be self-contained, you don't have to refer to something else, right? Okay, so let's move on. Image enhancements, we were talking about, first we looked at some of the filters that does smoothing or denoising. Then we discussed about boundary issues. Then image enhancements where you would use gradient information and Laplacian information. These were the instances that we had looked into in the last couple of presentations, right? Average filtering, we anyway discussed earlier itself, but just an illustration here. So wherever you would like to find out, you would take a neighborhood, you would figure out across which neighborhood you would like to compute this averaging, perform this averaging. So accordingly, you would take the window, will have equal weights for everything. The center one would be the one which you keep at the pixel where you would like to compute it. Then you multiply the corresponding elements, right? And then sum them up and divide by, of course, the number of pixels or which you did the averaging. Same thing with non-uniform weights, except that now the nearest ones you give more weightage to whatever pixel intensities are coming from them. Let's say this is one possibility where you give a weightage of 6 here for that pixel where you are centering it, 4 for the immediate neighbors, next second order neighbors you would give 1. Sum anyway is 16, so you are dividing it with 16. That was an empirical weight, that's where you have empirically set up those weights. You could in fact, for example, use a Gaussian filter for deciding the weights. Okay, so for example, here you could see 1 by 2 pi sigma square into e power minus x square plus y square by sigma square. Okay, and this is how you would now you figure out what would be the sigma value. Accordingly, you would get the distribution, you discretize that distribution, and that would give you the weights. This essentially would be the normalizing factor that you would get, so that the entire, for example, when you are applying it in a uniform one quick check that I would always do is you just see what happens if you have a region which is of constant intensity and you are applying this. So that would give you the intuition about it. For example, then whichever intensity is there at that pixel should retain. That means if you now sum up everything here, this is 16. When this is 16 and then the intensity is I, for example. So 16I by 16 would again give you I there itself. So that's one quick check you could always do for these windows. And anyways, all these are symmetric masks if you look at them, and thus convolution and correlation means the same there. Okay, usually when nothing is mentioned, you could here in this course you could consider it as we are referring to correlation itself. Okay. So then, unless I would say that this is the mask, it is convolved with a mask. If I give you, or then that mask you need to flip and do the stuff. Anyways, as we see, have seen most of these windows, most of these masks are symmetric, so that it doesn't really make any difference there. Okay. Now we were plotting here for sigma equal to 2 versus sigma equal to 5, where you are using a 30 by 30 kernel. So this is a 30, you could see 0 to 30, 0 to 30 here. As you could see here, when you have, these are almost 0, okay, when your variance is small. On the other hand, it's spread over lot more values here, okay, and then this is becoming 0. So one default value that, for example, MATLAB takes is 2 times ceil of 2 sigma plus 1. 1 is for the middle one. On one side you take 2 sigma, and the other side you take 2 sigma. Anyway, this being integer, if you are 2 sigma is going to be a non-integer value, you approximate it to the nearest integer on the higher side. So that's why you are taking ceil there. But again, you could always play with this by giving, for in case of MATLAB, you give filter size and then you mention the filter size there. Then another issue we were talking about is discussing about, yeah, any questions so far? This is otherwise going as a monologue. Do you have any questions so far before we move to the boundary issues? Particularly, I would like to hear from those who haven't done computer vision, because yeah, again, the next part will be a new one. Okay, frequency domain analysis and all we haven't seen. Only this part you see some overlap. So I would like to particularly hear from those who are from MTech. Okay, and BTech second year, third year students. Couple of students are also, few students are doing, right? 3 students are doing. So do you have any questions? Is it clear? No one have any questions? Yeah, Nutana.
It's clear, sir.
It's clear? Okay, good. MTech students, anyone? I would like to hear the voice of at least one MTech student. Hope there are MTech students in the class still.
Yes, sir, it's clear, sir.
Okay, good. Just stop. Don't hesitate to ask if something is not clear. Okay.
Okay, sir.
Right. Yeah. So then boundary issues is something that we were discussing. The typical one you would be considering is the middle one, same. So you are giving an image of an image I1 of size, let's say n by n. You would, even after applying this convolution, you would prefer having the image of same size. So that is when you would be following this middle one. Okay. And then you could already see, for example, if your mask size or the kernel with which you are convolving or correlating is 2n plus 1 by 2n plus 1, what would be the additional boundaries that you have to consider here? So I am telling you that let's say the convolving kernel is of size 2n 2w plus 1, maybe n, maybe you are using it, we are using it for the image itself. So let's say that size is 2w plus 1. So how many additional columns and rows I have to consider on one side here? For example, how many additional columns would come here to deal with?
W.
Sorry.
W.
Right, you get w here. So overall how many rows would come, how many rows and how many columns overall would come for a given image now?
Maybe 2W and 2Ws.
Right, 2w rows and 2w columns would come. On this side w, on this side w, this side w, this side w. These are the rows and these are the columns. That's what you would be getting there. Okay, right. So then that's what exactly, then how to, what value should we assign to those padded rows and columns? This is what the different possibilities are there. If you consider that line, okay, until which the starting column, if you consider, and if you are repeating, reflecting them all, that is one way to do. Perhaps that makes sense in many cases. And suppose in your image you already have, for example, your original image is somewhere in the middle and all these are zero, for example, at least w columns are already zero, then it is as good as keeping here. So anyways, this also comes under boundary conditions. Also, if you are taking derivatives, then you would also look at it as Newman boundary conditions and Dirichlet boundary conditions. Those things also would come here. But anyways, for the time being, yeah, discussing it in these terms is good enough. But you just need to be careful and what is the purpose of it and what's the application of it, and what's the type of kernel you are applying, and what is your application. Those things you need to keep in mind. Okay, in case if you are facing some problem, that's something where you need to take a look at. Okay.
So,
So can you give a small example for circular padding?
Means how we do circular padding, yeah?
Yes, sir.
Okay. See, that we would do, as I was mentioning earlier, you do it when you are actually looking at some frequency properties. That's going to make a lot of sense there. So see, so frequency spectrum means usually that's DFT, right? DFT, you have a repetition is there, correct? So suppose you have elements, so it's equals, let's say there are n elements, okay? Consider a 1D signal. You have n elements. So when you are computing DFT, you implicitly assume that this is a periodic, okay? If you have an FIR signal with n elements, you consider that to be periodic. So that's repeating, isn't it? So in that case, what you do is you append, you treat it as if it is a periodic signal. So exactly, you would be using the same thing when it comes to circular. So for example, in your image, it's as good as placing an image. This F is there, right? You place one more copy of F here and one more copy of here. So now it is, it being a 2D signal, this is periodic in both X and Y. So it is equivalent to, so what would happen then if you are keeping one more copy here? So then this element would come here, for example. And then wherever this is ending here, for example, this column, this column would come here. Okay, so it's as good as keeping one more image here and then looking at this here from this direction, and that
Okay,
would be
sir,
your
got it.
padded thing. Okay, this is what the theory says. I would just would request you to play with this in MATLAB. You just simply use it, take an image, and you do for filter, and then you see when you are using this, for example, this circular padding, just look at the image what it is giving. Just in case if you come across something different than what we have thought right now, let me know also. I didn't experiment myself with this is what I understood. So you please check with MATLAB where you give the padding as circular and see whether this is what is happening or not. Okay, is that clear?
Yes, sir.
Okay, good. Anyone have any other doubts or comments here? Okay, then we will move on. See, another nonlinear filter is that one would be using is median filter. And of course, there are many other filters also, min filter, max filter and all. Particularly when you have a salt and pepper noise, this is quite effective. But again, you have to be very careful while using it in the medical imaging context. See, there could be somewhere a tumor, let's say, that is giving you a completely different, a small tumor giving you a very different texture. So if you are using a median filter, you will completely, in the output, you might completely remove that information altogether. So particularly when if you are considering a larger window and doing it, you might lose a very potential crucial critical information there. So anyway, we just discussed it. You have to see, that's why I'm telling you, there is no universal prescription here on which filter is good and which one to use. You need to look into the context on what exactly you are looking. So what's the nature of image that you could expect here? What's the nature of noise you could expect here, and accordingly look at it. Okay. So
Sir,
yeah.
sir, how do you know that whether it's a noise or sir, like you told that it's a tumor? Suppose I don't have any background
Yeah. Yeah.
information about the image, whether
Yeah.
to how to know that it's a
Then,
noise or it's
yeah,
a tumor
then
like.
don't go for median, particularly in medical images, don't go for median filtering at all. This is very dangerous one, because that could completely remove you something which is the information is there. See, for example, what could happen is, one example is, let's say multiple sclerosis is one kind of brain abnormality, where what you would be getting could look like almost like a noise, for example. So from that application, you know that this is not something you should not be going for. Okay, there could be another instances where you are when you are taking an image, you are more looking it into a statistical characteristics and not for detection of the nature of object that you would like to detect is not something which will be very sparse, if that you know it. Okay, then you may go for a median filter. But if what you could expect there itself looks like noisy thing, even if you remember the mammographic images that we have seen earlier, with and without tumor, and then benign and malignant tumor, we were taking a look at some of those images. So if you apply median filter, probably you would lose important information there. So very rarely you use people using median filter for medical imaging. If you are using it, then the context should be, as I'm mentioning, should be somewhere where you already have prior knowledge that this would be something which will not be like spread here and there sparsely, but would be continuous. Does that answer your question?
Okay, sir.
Yeah.
Yes, sir.
Yeah, it's very rare. I don't remember using so far anywhere this median filter as such for medical imaging. On the other hand, applying Gaussian smoothing is quite common. Okay, right. So median filter, we just how to do that. But anyway, I just included it because later if you are going to use other computer vision applications, that's where median filter perhaps would play a vital role. Even SAR images and all, and yeah, those satellite images which are captured and all. Sometimes during the transmission and all, that kind of noise that get introduced could be salt and pepper. So when you have such prior knowledge, this is something you would find out that this works quite well. Okay, then we just discussed for the sake of completeness the properties that you could expect with these filters. So when there is salt and pepper noise, there is only values sparsely getting affected. So this is one case here. Now if you are applying median filter of, let's say, 3 by 3, okay, now I want to figure out what's the value here. So what I would do here, I would consider one neighbor left and right of it, and then you order them either in the ascending and or descending order. You take the middle value. Obviously two of them are same value, so that value would come and you will get rid of this mask. So you could see here there is no smoothing or blurring effect that would happen in case of a mean filter. And another thing is it preserves the edges quite well. So next step was this, where suppose when you are applying median filter at this point, right, you have this value, this value, and this value. Out of them you order them, and so this would remain same. Similarly, if you are applying here, two values are at the same and the other is one, so this edge has been nicely preserved here. So the second point is edge gets preserved quite well here. Third point is new intensity values are getting introduced here when you are applying a mean filtering. But in case of median filtering, all you are doing is you are looking at all its neighbors and of course that value itself, and you are picking one when you that one which lies in the middle of it when you are ordering them, okay, in ascending or descending order. So it is not going to introduce new intensity values. Okay, that's something perhaps maybe histogram equalization, I don't know whether it makes sense or not. Okay, that's at least that's the property wise, that's the property. Right, another example where you could see this could make a lot of difference. Okay, so that's all about averaging filters, I mean smoothing or image denoising filters. Any questions so far? Any other questions? Okay. So then we will move on to the gradients. Okay, another information while you are doing enhancement is keeping in view of the gradients. Okay, gradients are essentially giving you the boundary informations. So basically if you are dealing with the derivatives in either x or y directions, that's you refer to as derivatives, right, or edges in a way, derivatives. And then a vector of all these derivatives in your orthogonal coordinates. So suppose if you have a image in 3D, so your gradient is nothing but a vector containing dou f by dou x, dou f by dou y, and dou f by dou z. So this is what you refer to as gradient. And from there you could figure out, again coming back to 2D, you could figure out what's the direction of it. Let's say here you have an edge. Of course, this is being again, one thing that has to be very clear to you is, are we talking about the gradient or are we talking about the edge? Because these two are related at the same time, orthogonal to each other. So this, for example, is a vertical edge, but but the gradient is horizontal here. Okay, that distinction has to be clear. So you could see here, for example, if you are moving along this, right, then what would happen? This is your y. So if you are moving along the y direction, there is no change across the edge. So in this particular image, so your dou f by dou y is 0, but the maximum change occurs when you are moving in this particular direction. So what you have is dou f by dou x here. Okay, anyway, that you are looking in only two directions, dou x and y, orthogonal orientations you are considering it. So when you have a vertical edge, you have a gradient which is horizontal. Similar analysis you could do for a horizontal edge, which has gradient in the y direction. And suppose you might have an edge something like this, so then you would be having both vertical gradient as well as horizontal gradient. Now the strength of your gradient, to know that, this is what you would be doing: square root of dou f by dou x whole square plus dou y by dou f by dou y whole square. So how is it practically implemented when it comes to people from computer vision background should tell us, how do you implement this gradient in practice?
Using difference property.
Hmm? Yeah,
Like we assume the differentiation
yeah,
to be.
differentiation is correct, but the gradient magnitude, how do you compute? There is one more approximation we were discussing earlier. So you won't be typically doing the square root of dou f by dou x whole square plus dou f.
We can take the Manhattan distance instead.
That's right. That's right. So you take an approximation to it, which is absolute value of dou f by dou x plus absolute value of dou f by dou y. Anyway, these are to an extent already discretizing and doing it. There is some approximation already here. So you would simply go with the Manhattan distance. Okay, dou f by dou x plus dou f by dou y, both each absolute values. Although it is not exactly same as this L2 norm, it would be a value close to this. Okay, and then computational wise, that is less expensive, because you don't have to find out squares, then sum, and then square root. You just need to do sum of two numbers. Right, that's what you typically do in practice while you are implementing image gradients. Right, I think you had some assignment also in computer vision related to this. I don't remember exactly, but I guess so. Okay, so in order to find out now the angle at which this gradient is there, would be, now this is, for example, dou f by dou x, this is dou f by dou y. So tan theta equal to derivative in the y direction divided by derivative in the x direction. So theta will be equal to tan inverse of dou f by dou y by dou f by dou x, right? So what's the range of theta values you could manage to get with this? Range of theta values?
Minus pi by 2 to pi by 2.
Minus pi by 2 to
Pi by 2.
okay. Anyone can anyone?
If it's arc tangent, then minus pi to pi.
Yeah, that's right. So is the difference what he said is clear to all? So what's the range tan inverse would give you typically if you are not keeping track of the sign information of both numerator and denominator separately? What would be the range of values that you would get with a tan inverse function?
Minus pi by 2 to pi by 2.
Right. What happens if you are explicitly keeping track of numerator and denominator signs, not combined?
Minus pi to pi.
Right. So it's not arctan. Suppose if you are using MATLAB, there is some function called as do you remember what is the function in MATLAB?
A tan.
No, a tan is the
No.
first case. Second case, what is the function?
A tan 2.
Right. A tan 2 will take your numerator and denominator separately, or denominator and numerator. Look at the order, but that's what it takes separately. So that then your range would be from minus pi to plus pi. Okay. Yeah.
So how does taking separately create a difference? Like I did not understand.
Okay. Yeah. See, I have tan inverse of, so it's a good point. Let me check if I could write here. Is question clear to the rest also? How is it going to make a difference? So this is my x. Oh, this is my y. Suppose here theta is there. Okay. Now I would like to find out this theta. Now one, and then there is, for example, okay, that is one possibility. Let me draw this also maybe. Okay, yeah, I assume that these are parallel lines. Somehow I am not, although I'm not drawing them exactly. Okay, so these are, so which case shall I consider? Let me consider a case this, okay, where my x is negative, y is positive. Okay, then another case where x is positive and y is negative. So suppose both might be tan inverse of minus, assume that my x and y are equal. Okay. If I tell you tan inverse of, so assume that these values are all 1. Okay. This is anyway minus 1, 1 here. This is 1. This is minus 1 here. If I tell you tan inverse of minus 1, can you tell me what's the angle now this is equal to? Tan inverse of minus 1 I have given you.
Minus 45.
Right, minus 45. But now if I tell you tan inverse of, assume that I would give you the numerator, the x value first. On x I have minus 1 and I have y equal to 1. Can you tell me now what is this value? Can you tell me now what is that value?
135, sir.
Good. This could also be equal to 135, right? Minus 135 is true here also. So this, whether this is this value, okay, or this value, you would be able to read. On the other hand, if I give you tan inverse of 1 and minus 1, what would you tell this value to be equal to? My x value is 1, y value is minus 1. Then what is that value?
Minus 45.
Minus pi by 5.
Correct. So do you see now, if I'm explicitly keeping track of my of the signs of my numerator and denominator, I am able to extend the range to minus pi to pi. Is that clear?
Yes, sir.
Right. Is it clear to everyone? So that's why usually you use a tan 2 function here. Right. So those were the definitions of in the continuous time domain for your dou f by dou x. Okay, now you need to do it. This is the definition. You could say limit epsilon. You change, for example, I would like to find out the derivative with respect to x. So I'm going to make a infinitesimally small change in x. Okay, so one is x plus epsilon and another is x itself. Then I compute this function value at both these points, subtract them, and the difference x plus epsilon minus x. Okay, this is the definition of a derivative in the continuous time domain. Now we are in the discrete time domain, so you cannot have this, cannot compute this value at any epsilon, but it, for example, can be 1. So that's when this would become f of x plus 1 comma y minus f of xy by x plus 1 minus x, which is 1. Of course, this is called forward difference. And now you know, we anyway discussed in the video also, if you are using, instead of say for example x here, x minus 1 here, okay, then x minus of x minus 1, right, that would give you backward difference. Now you consider in your epsilon to be 2 now. So then what would happen? So let's say I computed it one at x plus 1 comma y, another at x minus 1 comma y. So in order to compute the derivative value at x, I'm looking at the function value at x plus 1 and x minus 1. Okay. So in that case, that would be equal to f of x plus 1 comma y minus f of x minus 1 comma y by 2. That's how I compute the derivative. Now if I want to, so basically this would be then the function. If you are computing, for example, this is for what? Is it a forward difference, backward difference, or central difference?
Forward difference.
Right, forward difference. So yeah, by the way, in the video, I was marking there in the wrong place the origin. If you notice there, this origin is, for example, at +1 here. Okay, is it not so? X plus 1, you just take a look at that. Where is the origin here? Say I'm keeping here, okay, then f of x minus f of x. That depends on where I'm keeping my origin. Actually, you need to look into that. So for example, if my origin is here, okay, then it is f of x plus 1 minus f of x, okay, by 1. So suppose if I am keeping my origin here, then it is f of x minus f of x minus 1. Then that would be the backward. So I had to explicitly mention here because otherwise you won't know where to keep the origins are matching. So anyway, that's why in practice you would rather go for a central difference based derivative, where you are using 1 by 2 times of f of x plus 1. So this obviously the center of your window, 2 by 2 window itself is your center. Right, then these are other gradient operators we are calling here. Again, be clear with horizontal edge is equivalent to vertical gradient, and similarly vertical edge is equivalent to horizontal gradient. So essentially, if I ask you among these two, let's say Sobel, which is the mask that computes you horizontal gradient, what would you say? Is that the first one or second one that computes horizontal gradient? I want a mask that can give me the horizontal gradient. So which one of those, is it the first one or second one in the last column, last row? That computes me. I want a horizontal gradient. Dou f by dou x is what I want.
The first one.
The first one gives you horizontal gradient. Is anyone fine with? Is everyone fine with it, or any of you have an objection?
No, so second one.
Second one, horizontal gradient and
Correct. See, this is a, for example, when you have an edge here, what would happen? The information on both sides is different. So this is essentially so this is equivalent to having an edge here. If you have it, information on either sides would be different. Okay, that's because there is an edge there. So that's what essentially look at here. For example, to begin with, I think you look at here. If you are doing it simply here, that is equivalent to finding out a which is it a forward difference, backward difference, central difference of derivative, just that mask. Come on, what is that derivative that if I have only these two values, okay, and the rest you assume to be 0, then what is that? What is the difference scheme you are using here to compute the derivative? No, just now we have seen, right?
Twice the central difference.
Right, that's the central difference scheme. See, essentially what you are doing here in this mask, you are doing suppose I want to find out the function value at this point, okay, So had it been simple central difference scheme to compute the vertical gradient, I would have used this and the rest would have been 0. Now you notice here, I am computing a derivative here as well, and then summing them up. Or in other words, this is equivalent to some kind of smoothing on the derivative. That's how you could think it of. So essentially you are computing derivative here, derivative on the left side, right side, in the middle, then you are summing them up all together. In a way, this is equivalent to the averaging is what you are doing here. So there is neighborhood based averaging is also there. At the same time, derivative is also you are computing. So this would essentially find out a horizontal edge. That means your grade, it gives you a vertical gradient. Same case here, but you could see here, suppose if I am giving this is equivalent to, once you find out a derivative here, you give its value weight of 2 and you give value of weight of just 1 to its neighbors. That's essentially what you are doing here. So this is a weighted average. Okay, you might be wondering why there is not multiplication there. Again, I would always refer you back to looking at what would happen in case of a uniform region, and then all that uniform region to have the same input, say output same as the input, your the mask sum has to be 0. That's all. So anyway, the mask sum is 0 here, so that's why even you are multiplying it with 2 doesn't matter, you still, this is getting compensated by 2 here. Okay, so that's why you don't have any other multiplication factor coming there, right? You are giving double the weight to the center pixel vertical gradient and giving weight of 1 and 1 to the neighborhood things. Is that clear? So there is a kind of smoothing as well as finding out the derivative when it comes to Sobel edge detection or Robert edge detection. Is it clear to everyone? Okay, I hope so. So then similarly, you are taking a look at here. If you are for some application, this is not for gradient computation, but you might want to look at edges which are there diagonal. So you could see here, then you would, the same logic would apply here, except that this is your edge. Now you could, same values are given 1 minus 1 here. So this is how you are looking at diagonally. Okay. Suppose now you are giving the same logic as the previous slide, but you give a weight of 2 here to this. So 2 minus 2, this is 1 minus 1, 1 minus 1. Now this is your edge, or the gradient is in this direction. That means if you consider this as your x-axis, this is kind of 45 degrees edge for this one, and this would be minus 45 degrees. So this, again, you are trying to find out these edges. So this is one diagonal, right? So same here, this is your edge. Okay, you give double the weight here, minus 2 2, this is minus 1 1, minus 1 1, right? Is that clear to everyone, the diagonal edges also? Okay.
Sir,
Yeah.
sir, in the case, like when we are convolving or correlating a kernel with the image,
Ah.
to save the number of operations, to preserve the number of operations from n square to 2n, we can split the kernel in
Right.
x and like we can split the kernel from 2D to 1D from x and y.
Correct.
So like how can we do for this Sobel and Privet? Like what are the x and y kernels for that?
Right, just 1 minute, let me what are the extent, yeah, you I don't exactly remember that, but I, if I am not wrong, it should be having just 1 minute, pause. Mm, uh, I just paused my thing. Pause recording, meeting, disable annotations. Yeah, okay, here. Yeah, sorry. So see, yeah, that should be possible with this. So, see, the question is, you is many times you will not do a 2D convolution, but you do a convolution in X and convolution in Y separately and combine them, right? So think about it. It should be possible here, I hope, for the Privet and this. I don't know exactly how. uh, so So basically, question boils down to how can I write a 3 by 3 matrix as a multiplication of a row matrix and a column matrix, correct? Is that correct? So
Yes, sir.
why don't you try writing it this way? Just yeah, you answer this question to me. Yeah, you yourself try to answer this question to me. Okay, that matrix is given to you. Then whether is it possible to write it that way or not is the first question, right? Just you check it out. I guess it should be possible for Sobel and Privet. That's what I guess. You try it yourself and let me know.
Okay, sir.
Okay. Yeah, I think that's something I haven't explicitly talked about in the in my lectures in the previous ones, is that another important property while you are looking into these masks is that you will see if it is possible to write them as a combination of a row vector and a column vector, so that you could instead of doing it all n square locations, you would do only in n locations in one case and n locations in the other way. So in other words, you do horizontal convolution and then vertical convolution or correlation, whatever you call it. Okay, so that's called the property of separability. So that's something you would explicitly exploit wherever it is possible. So certain cases that might not be possible. Well, the way I would justify here, not exactly going for it, is anyway I just have to do it 6 locations here, multiplication 6 multiplications I need to do here. If you observe, even if you are separating them, row wise 3 multiplications I have to do, column wise 3 multiplications I have to do. Is it not? So do I really need a separable property here to exploit?
So, but computer will, like, even though it is 0 for us, but like
Yeah.
if at all
No,
we
no.
are
You implement yourself there. You could you could exploit this property while you are doing the convolution. If you are writing your own code, you could always exploit it here. See, the multiplications there anyway. The moment it is 0, there is no multiplication as such happening there. So as such, yeah, if you like, yeah, just check if there is a if it is possible to separate them. Even if it is not the case, you could always write your code. It is possible to customize your code if you are writing your own code, that there are only 6 operations even with these masks. Is it not?
okay, yes, sir.
Yeah, because anyway,
Sir,
yeah.
I able to, I mean, column vector -1 in case of Robert's horizontal kernel -101
Yeah.
is a column vector, 111 is a row vector. Then I
No, the question is, are they horizontal and vertical edges, right?
no, this is what Suman said, that is there means it's about separability.
Right.
Means if the column vector is -101 and row vector is 111.
-1.
-101 is column vector and 111 is a row vector.
-101 is the column vector, and then
1111 is row vector.
1
1
one more one, huh?
yes.
So check. So this is 3 by 1, right? And this is 1 by 3, should give you -1 into 1 -1, right? -1 into 1. So basically this whole thing becomes -1. They're happening here, right? Yeah, that's good. So this is all becoming 0. So then this is getting 1. Yeah, this is good. Okay, suppose now I want to get this one. I should just, I think if I make 1 to 1 here,
It's correct.
right? That you should be getting this.
Yeah.
Okay. Does that answer your question, Sumant? I think now Sumant is
Sir,
not.
actually,
Yeah.
I just checked in the internet. Like this thing is possible when the kernel is, like, we can separate when it is diagonalizable. I
Right.
mean,
No,
and but
is it working out? Let's go to the math a little later to the theorems and all. So, but is
yes,
it
sir.
not giving you the row and column vector? There is
Sir,
an example here. So, is it not this vector, column vector and row vector is giving you that property? So you are able to separate, right? This matrix, for example, this is what I want. your column vector is -1, 0, 1, row vector is 1, 2, 1.
Yes, sir.
Similarly, if it is 1, 1, 1, you get this.
Oh, yes, sir.
Okay. Hope
Yes,
you
sir.
are happy now.
Yes, sir.
Good, good. So for those of you who have not seen this separability earlier, so this is where instead of multiplying everywhere with a 6 by 6 matrix, what you would do is you would do row operations. You do them separately. In fact, see, now you could write this matrix as multiplication of these two, right? So you could first simply do these two. Okay, you could multiply it with the column vector followed by the row vector. It gives you the same way. So that makes, even you could see now, see, this operation happens only across your column. Okay, it doesn't nothing is going to change in your output across the rows. So how can you exploit this property while you are doing a parallel programming? Now you have a parallel computers, GPUs, everything. Okay, now suppose when I am writing this mask as multiplication of -1, 0, 1 with 1, 1, 1, as you see here, right? So how do you exploit that now in your parallel programming? Hello?
We'll first do for horizontal and second we'll do for vertical
I
separately.
would like to hear from others also. I know it's clear to you, so I would like to hear from others also. So how are you going to exploit this now? I give you a parallel program. Like, you just have to tell me how you want to implement, and you have a magical box that gives you the code for it also. Okay, I have an n by n image. Okay, I wanted you to apply, find out this, let's say, horizontal edge detector, private horizontal edge detector. And how do you know? I'll tell you. Tell me how you parallelize your coding. Then the code comes out. Okay. So how do you parallelize now? Come on, this is not a tough question. It's a trivial question only. Almost the answer is something is there while we are discussing earlier also. Is it, maybe my question would have been not clear? Otherwise, the answer is straightforward. Sashwat?
So can you repeat the question again?
Yes. See, I have an n by n image. Okay. I want you to apply now the private horizontal edge detector. Assume that multiplication with matrix is very cumbersome, or I don't want to do it. So I divided them into these two, -1, 0, 1 and 1, 1, 1. Okay, multiplication of both would give me the required mask. Now I want you to you could do parallelly multiple processes. You could call multiple threads. Okay, now how do you implement your code to exploit this, exploit the fact that you just have a vertical and a horizontal vectors there?
So we can compute each of them separately and then
Yeah,
add
be more
finally.
specific. Each of them means, what is it that you parallelize?
Sir,
What is it?
The
we
horizontal
convolve
one
with the
first
matrix.
Horizontal.
and then the vertical one.
Well, that even for a vertical vector, okay, this vector -1, 0, 1, how do you parallelize your operation, applying it throughout the image? Is there a way you could parallelize this?
So we
Yes.
can directly convert, right?
Yes, I want you to implement it, but is there anything that you could exploit while you are implementing that parallelization? How can you parallelize your operations of applying it throughout the image? Sumant, you could also chip in if you want.
Sir, I'll simply just multiply and add.
No, no. Just forget about the rest of the things. You multiply but add. You could do operations parallelly. That's what I am giving you now. You could call each thread for some operation. So how do you then make use of that?
So then for the one image, we will run it in all the threads together.
So yeah,
And
what is it that you run in each thread is my question. Others also give it a try. It's not a difficult question at all. Samir, any thoughts about it? What is it that you run in each thread? You could run, you need to apply this mask across the whole image. Okay.
Yes, sir.
So what is it that you do? Or what is the operation that you do in each thread? That's all my question is.
Multiplication.
Multiplication only, sir.
Maybe I'm not specific. I'm afraid I'm not clear then. Say, let me give you this way also. Okay. I have an image of size 100 by 100.
Yes,
Okay.
sir.
I have 100. I will give you 100 threads that run in parallel. Okay.
Yes, sir.
How do you implement now?
so for each region of the image, we can do like each pixel we can do like in.
Be more specific. I'm giving you the numbers also. Just take those numbers also literally. I have an 100 by 100 image. Okay. I give you 100 threads now that can run in parallel. What is it that you give to each thread?
So we multiply all of each pixel with the product of these two in every thread.
No.
So
What
each
is
of the
Mix up
10
the
cross
threads
10.
each of?
So the 10 cross 10, like we have 100 threads. We have a total of 100 cross 100 image
Right.
size. So like if we divide the image into separate parts, so each thread will process only a certain region of the image.
Can you be, means these numbers also I have given purposefully the numbers. I'm telling you, can you simplify it? Of course, that's all.
Yes, sir. So
100 by
10 cross
100
10.
100 by 100 is the image size. Okay. You need to apply just this operation. Forget about the other one, just this operation. And then finally you should get the output for the entire image and 100 by 100 image and 100 threads. Tell me a simple way. You don't have to know parallel programming course there. You could think about it and you could tell it quite easily. Just a simple logic.
Bottom element minus top element.
Yeah, that is true. That's what you would be doing. But how do you distribute this program to each thread? That's all. This operations.
So what we can do is like for the image, all the top ones we can take together.
What happens?
Like we can compute all the pixels which are going to be multiplied by -1. We compute all of them together.
Okay.
Similarly for 0.
Maybe I will make it more specific. I think then you will be able to answer it without any difficulty. See, my image is 100 by 100. Okay, something I'm not going to draw here 100 by 100. But suppose if I want to compute here the value. Okay, at this pixel. So who are its neighbors while I'm applying this? Is it everybody is his neighbor?
Sir, I'll use the row vector and column vector for that particular element.
Very good.
And use it in a thread.
So all you need to do is you just divide the image by column wise. And for each column you apply this. Because here it looks into only its vertical neighbors, not the horizontal neighbors. Of course, you could divide into 10 by 10, but this is more efficient. You just divide your image into column wise. You dump to each thread one that column and this kernel, let it do the operation, you collect it, and then you fix it. That's all. Is that making sense? And you do, when it comes to, for example, this mask, you divide the image row wise here. For each thread, you give this row. Okay, you get the output. At the end, you combine all those outputs. Anyways, if you, means it's easy to get it. Is it not? Is it clear? Shashwat, do you agree with that?
Yes, sir.
Yes, sir.
Okay, yeah. This is what anyway, if you are trying to implement your program more efficiently and not let the GPU or your program, CUDA program decide it, this is how you would be doing it. So you just simply need to look at, okay, I think we are running out of time. Okay, so hope this is clear. I will move. That's anyway, if you get it, it's good. If you don't get it, you think about it little later. Okay, that's not difficult thing to analyze. Right. So then we were, any questions so far before we are moving further? Any other question? Quick questions?
Sir, how can you like divide into a row and vector for a diagonal edge detection?
No, I'm just talking about this only. That's why I was very specific.
Okay.
This is how what I'm giving. See, for example, a diagonal edge, if you could write it something like like a multiplication of separability is there, that's what you could exploit the parallelism there. That's all I'm saying. If your diagonal edge, if you can write it again as you mean, for example, here, is this what you are talking about?
Yes, sir. Yes, sir.
Yeah, just check if you could, if there is a separable property to this matrix is there or not, you check it out. Okay, if there is a separability property, then that's when you could exploit this.
Yes, sir.
Yeah, good. So any other questions? Okay, I think this presentation also went for almost I think 50 minutes now. Okay, so then this derivative, we could see that, see if you ask any one of us, where is the edge here? Okay, all of us unanimously would say that here is the edge. Okay, uh, but on the other hand, if you are taking a simple, so this is essentially now, even if it is slightly corrupted by noise, okay, we will be able to nicely say that here is an edge. But if you are using an operation like forward difference or backward difference, this also would contribute to lay, so the edge got buried down into the noise also here. Okay, so that you won't be able to say. So what you would typically do is you would apply a Gaussian filtering so that this gets averaged out. Okay, if you are applying a Gaussian filtering, anyway we started from this point because this window, otherwise if you are having here, you need to make some assumption here. So assume that you are okay, you have enough, you could leave a part of it, so there is no edge in the boundary edges, we don't consider. So if you are doing this Gaussian smoothing here, then you will be getting this. And on top of it, now if you are applying a forward difference, backward difference, or central difference, whatever, you would be getting this nicely. And then the peak is telling you that there is an edge here. Okay, so that's what would happen. That means in practice, before you apply a derivative, you would be also applying a smoothing operation. Gaussian smoothing, let's say, is very common. Now if you are applying, first you are smoothing, then applying a derivative. If you have an n by n image, this n square number of operations you are going to do twice. On the other hand, you could exploit the properties of this convolution, where it has an associative property which tells you that finding out the derivative of h convolved with f is equivalent to convolving f with derivative of h with respect to x. So for h, you already, if you compute the derivative of it, that's what, this is what you would be getting there. So simply now you can, instead of convolving with a Gaussian to do smoothing, then followed by another kernel, you simply right away convolve this image with this kernel. So then this is how you would be doing in practice. Okay, I guess everybody is free and I could extend it a bit. I hope there is no problem with that, right? I just would like to finish it off. There is not much again, with just this and then followed by the Laplacian. Is everybody fine with it? Or don't hesitate to say that if you want a break or something like that.
So you can proceed.
Yeah, okay, good. So the others who are quiet, I assume their acceptance for doing this. Okay, let's go ahead. Otherwise, this also getting stretched for too long also makes you feel boring. So let's finish it off. Anyway, the flow is there, so let's finish it off. Okay. So this is what you would be doing in case of a derivative. If you want to do smoothing followed by derivative, you would be simply convolving it with this. Again, you could also notice that convolution with this is exactly equivalent to correlation, because this is again symmetric. Okay, again we are plotting here a circle in a continuous thing, but in fact that's also you would be in fact having their discrete values. Now, if you want to compute a second derivative, what you need to do, you have to take dou by dou x of the whole stuff. So again, that's equivalent to, again, you exploit the associative property, and that's equivalent to just taking one more derivative of dou h by dou x. So that's how it looks like. Okay. And that's the, in 2D, that's the inverted Mexican hat, right? So you then, if you look at what is going to happen in about a edge here, is you would observe a zero crossing there. Okay, so this is, so if you are using a first order derivative, this is again, you know it from your calculus also, first order derivative, an edge is a sudden transition. Okay, that would be figured out by having a peak in your first order derivative. And in the second order derivative, if you are looking at this, would, you have an edge where there is a zero crossing. You could take even a simple example, you take some numbers and do this out, you would also figure out the same thing there. Okay, I leave it to you also to have some intuition on why the derivative of Gaussian is a curve like this. Okay, you just spend some time, I want you to think yourself, then you would get something like this. And then you are taking derivative of this, why does it look like this, why it is increasing in the beginning like this, and then reducing, and why do you have a peak here, that you just think about it. It's not difficult. So having some intuition about how those, why you are getting something would help you later. If you even forget the shape, you could intuitively draw it yourself. You don't have to remember anything. So you just spend some time with it, figuring it out intuitively why it is like that. Right. So the same thing, now we move to the 2D part. Let's say this is a, for example, derivative in the x direction, correct? Is it not a derivative in the x direction? Yeah, horizontal, yeah, derivative in the x or y. It's a derivative in the x direction. Okay, if you want to find out, this is 1 minus 1 mask, assume that. So this convolving with g, so g with h, if you want to do it. Okay, so basically you want to smooth the image, and that you want to find out a derivative in the x direction. So instead of that, now what you do, now you convolve the Gaussian with this h. Okay, that would give you a mask like this. Now, so you directly convolve with that mask I, that would give you a derivative that you obtain after smoothing a given image. Okay, similarly in the y direction also you could find out the derivative. Okay, so this you could see the differences. One is this exact means there is a variation here in the intensities. So that is telling, on the other hand, there is a negative intensity. Yeah, see, negative means the negative most, if there is a -1 there, that's what you consider as black, and one as bright, and then you keep varying it. Okay, whenever there is, so that's what you would be getting. You could, by just looking at this mask also, you could tell this is again a surface plot of it is something like this, and it looks like. Okay, so by looking at it also, you could say that this is trying to look at differences in this direction. Okay, that would essentially give you a vertical yeah, horizon. So that's a vertical edge, is it not, when you are doing it derivative in this direction? Just look at that, I might be wrong, just take a look into this. Right. So then we talked about sharpening image filters. So while you are trying to sharpen the image filter, typically what they will be doing is they would be using Laplacian also. And then you already know that a derivative can be expressed either as a forward difference, backward difference, central difference. You take again derivative of it. Then this I worked out in the presentation, right? So this is equivalent to, you sum the two. So I want to find out Laplacian at a given pixel. All I need to do is sum, for example, Laplacian in the, so second derivative in the x direction, assume that. So for a given pixel, you sum the intensities on both left and right, and from that you take twice the value of the intensity value at that pixel and subtract this from the earlier sum. That's what this is going to tell you. So I neighbor value, let's say the right hand side neighbor plus left hand side neighbor minus twice the value of intensity at that pixel. That will give you dou square f by dou x square. Same thing in the y direction would give you dou square f by dou y square. So you combine them both, that would give you, so now there is 2 times here, minus 2 of f of xy here, then minus 2 of f of xy also would come in the other one. So that, yeah, this is how you have this. So this would come minus 4 f of xy, and left, right, top, bottom, those 4 pixel values, you sum them up. From that you subtract 4 times the pixel intensity at that f of xy location. So that would give you this one. And then we have not done any thorough derivation way, but you could do similar lines you work out. Just not only look at immediate neighbors, but also look at diagonal neighbors. So then you earlier these values are there. So now this also you take to be 1. So this then would become minus 8 here. So that would give you this one is referred to as 90 degrees Laplacian. The other one is 45 degrees Laplacian, because if you keep rotating it by 45 degrees, you get the same mask there. So it's an isometric, what is it called as isometric, or what is the word used for it? I think that is there. Yeah, I think yeah, just look at the word. I don't exactly remember now. So it is isometric by angles of 90 in the first place, and next
Isotropic, sir.
yeah, sorry, not isometric, right? Isotropic. Second one is isotropic by 45 degrees, right? Clear so far? Anyone need a small break or something? Anyway, we'll otherwise also we'll finish in 10 minutes. We are almost done. Yeah, any questions so far? Maybe I hope at least there is some question here. Does anyone have a question in the slide? Now, what you would like to do here is you want to add this Laplacian to the original image. Okay. So then while doing that, you have here, for example, how can you get f of xy? How can you express f of xy in terms of a mask? So in other words, convolving with that mask should give you the same image. So how should be the mask? I need a 3x3 kernel. Okay. After convolving with that 3x3 kernel, I should be getting the same image. So how do I get that? Am I clear? I gave you an image. I'm
It
asking you
should be
to,
like a impulse, like the center one should be high and everything should be 0.
okay, then there is no high and low. Center one is 1, the rest is 0, correct? It's
Yes.
not any value doesn't give. High means, suppose if I keep there 100, it is no more f of xy, it is 100 times f of xy, correct?
Yes, sir.
So it should be, if I ask you for a 3x3 kernel, that would be, for example, 0 0 0 0 1 0 0 0 0, right? That would be the kernel to get the same image. So that you add here to the Laplacian. Okay. Yeah, there are different ways of considering this. Again, all this material for image enhancements, most of that I have taken, but from the Gonzalez and Woods. Okay, the book I was referring earlier, image processing. So you will find out all these figure 3.37 and everything is from that book itself. So if you want, you please refer to that as well to read it, or for more details also there. So essentially, they would also write this mask still give you the same behavior, even if you are, the whole thing is taken a negative sign here. So suppose this is nothing but -1 times, if you multiply all these masks, these are the masks that you will be getting. And in case if you want to add to the original image the Laplacian, you should be using this. Okay. So I was expecting some people would ask a question here, but yeah, I'm happy nobody, means it's easy for me that nobody has asked a question here. But if you still have any question, you could pose it. Does anyone have a question here?
Sir,
Yeah,
So what does the addition tries to do here? Addition with Laplacian, is it trying to highlight what we have extracted?
exactly. So wherever there are edges, so it is trying to highlight those edges in that. See, for example, you could think of my original image is from 0 to 255. What I will do now is I will add Laplacian to it and then again renormalize it. So my information is in edges, renormalize it to the range of 0 to 255 after adding it. So now the information which is there at edges is getting more highlighted there.
So, but this thing, the same thing is done by Sobel, Privet, and the other filters that we have also, right?
Correct. There is a slight difference. Anyone can anyone shed light on Sobel versus this Laplacian? That's a very important point you mentioned. That's an important question. Can anyone shed light on applying Sobel versus applying this Laplacian mask? What is the difference between them?
Sir, this gives corners also.
This is
This gives corners also. Corners.
well, that is not really true. I won't agree fully that this would give you. So if you recollect, since you have done computer, see the rest who haven't done computer vision, don't worry about these points. Okay, otherwise, see, after applying Laplacian also, we were doing certain operations to figure out whether it is a corner point or not. Even if I have an edge, for example, even if I have a very strong edge in the horizontal direction, Laplacian would give me very high value there. Is it not? Assume that I have only a vertical horizontal edge, okay, but that has a very high magnitude. So that would get reflected in my this computation. Whatever computation I am going to do here, okay, I mean let me change into pen mode here. See, assume that I have a horizontal edge, okay, then this value would be, if it is very high, irrespective of how its behavior is there in the vertical, it would still have a very large value there. Don't you agree with me? So I
Yes,
won't
sir.
fully agree that this is a corner, it gives you a corner response. But of course, when you have a corner also, you could get a high value there. That's a different story, but you cannot distinguish between corner and edge here in the Laplacian. So yeah, I'm coming back again to the question. What Shashwat was asking is, how is this different from Sobel? Can anyone Sobel horizontal and vertical edge I use versus Laplacian to find out detection of edges? So how are they different? Do you see any difference there?
Sobel gives the highest value, like the maximum value over there. But mathematically, if you see, and this Laplacian of Gaussian gives the zero crossing over there at the image.
That means, yeah, one is giving maximum, one is giving zero crossing. That is fine.
And this is
Yeah.
like it's like a blob detector.
Okay. So what?
It, like the smoothing operation over in this Laplacian is more compared to this Sobel or Privet.
No, I think you said exactly the opposite.
Okay.
There is smoothing happening in Sobel and Privet, not here in the Laplacian.
Yeah, sorry, sir. Like, I mean, yeah, other way. Yes, correct.
So that is why the earlier one you are taking as a mask, if you notice later, and then the Laplacian is used to highlight the edges in the example that we have taken. Is that answering your question, Ashwat? See, if you are using as an edge detector Privet or Sobel, right? So we have seen here that in fact this is using a smoothing over gradients here already. So had I been in case of Laplacian that just uses this information, doesn't use these two. in the formulation of Laplacian. But on the other hand, if you are using Sobel and Privet edges to find out the gradients, then there is some smoothing happening there. So it is less sensitive to noise. Okay. On the other hand, the Laplacian is more sensitive to any finer changes. So that's why you are trying to combine both. Okay. One as the mask and the other as to detect where there are changes.
So, sir, Laplacian, it highlights noise as well.
Yes,
in the output.
exactly. So that is why in the example that was given, you use it as a mask to get rid of noise. Okay. So is everyone on the same page? Is everyone getting the question that was posed there?
Sir,
Yes.
how exactly does Sobel and Privet reduce noise?
How? No. Can you repeat? How effectively?
How
Yeah?
does Sobel and Privet reduce noise?
Nice. Yeah. See, what is the, for example, you consider this horizontal edge detection. Oh, suppose if I want to find out gradient here, it has been only -1 and 1 is simply that would give you the edge, is it not? But on top of it, I am using the edge information at the left neighbor as well as my right neighbor here, and then summing up over here. So that is how you are not looking at the, in a way you are doing averaging of derivatives. So that should smoothen. If at a one point suddenly there is a derivative, since you are averaging out, that should reduce.
Okay, so if you use a bigger kernel size, then it will smoothen it even more.
Right, that is right. But I'm not sure. Yeah, that's correct. That's correct. I agree. That's right. Because it's averaging of gradients you are doing across your neighborhood.
So that means Laplacian also, like, we consider the nearby pixels too, no, sir?
Yes, but see here also considering pixels is different, averaging your value over it is different. See here also to find out derivative you do -1 here, but that doesn't in a way that's to just compute the value here, not at the values of derivatives at neighboring pixels. That is what, in addition to finding out derivative at that point, see, even if I am having this -1 and 1, if I take, that's the first step of your Laplacian. Take one more step, one more derivative, then it would be Laplacian.
Sir, so if we take a bigger size of the Laplacian kernel, will it kind of smoothen it, like
No.
with a bigger sigma value, bigger variance?
What do you mean by bigger? Laplacian is this mask only, right? How do you make it big? This is all the Laplacian is. There is nothing like a bigger mask here. You look at, that's all Laplacian is about. You can't make it big or anything like that. You just look at the pixels, 4 pixels, 4 by 4 means 2 by like 3 by 3 window is all you require for a Laplacian.
Okay. No, I thought like
No.
since it's a
So
hat,
no.
what if we increase the variance like that?
This is all your Laplacian.
Okay, sir.
So what you are looking at for a given pixel, you look at
Only
x
those.
plus 1, x, that's all. That's your Laplacian.
Okay, sir.
And of course,
Since it converges at the center, it doesn't smoothen it exactly.
Very good. Correct. That's right. Exactly.
Okay, sir.
Is everyone following the discussion? Or otherwise, please do.
Sir,
Yeah.
Sir, can you move to the next page?
Yeah.
Next.
Yeah.
Sir, in this, like, why have you used +5 instead of +4?
+5. That's what you wanted to do. F of xy also. So that is this mask.
Okay. You're adding this one also.
Exactly.
Okay,
Right. That's why you take now 4 -1 -1 minus. Yeah. I wrote it in the wrong place.
Understood.
You have to be x and y.
Okay.
Okay. Any other question here before we move further? You might be getting means I thought somebody would at least ask me and put me in trouble with -1 and +1. I was thinking for quite some time there. Okay, but nobody. Yeah, I think if you had tried to work out, you got that doubt. Like while you are using the -1 mask, you should be subtracting it from f of xy. Although it looks like f of xy plus Laplacian, you have to take a negative sign. Okay, that will be slightly, to arrive at that, it would be confusing. Since nobody has asked me that question, I am giving you a hint and you work it for yourself. Just look at whether, if you get a doubt on whether you have to take, see, one is negative sign means these are the mass that he's talking about. You take negative of this, that you will get here. So if you want to add to the image the Laplacian, if you are taking this original masks, you need to subtract that from the image in order to add it to that. So that looks counterintuitive in the beginning, at least to me. Then it becomes clear to you. Just take an example again. Your resort is a simple case where you take a uniform region. Okay, constant intensity is there everywhere. Then if you are applying this mask, now whatever mask you are getting, you should be getting as an output the input image itself. So for that to happen, how it should be, you think, you just you analyze that part and you will realize that you have to take a negative sign here and a positive sign here. Okay, I leave that exercise to you. That's the hint, that's the answer for it. I have given you the answer, except that I'm not again going into the middle details. That's all. Okay, so now it's a PET scan has been taken as an example. Then yeah, they were looking at analyzing the bone infections. Okay, so for that they want to highlight the bones, and with the PET scan there will be a lot of noise, and this is the whole body PET scan. They could hardly see, the lower part is not at all visible as such, and then the bones are also not in this region. For example, you could hardly see the bones. So what they did, they computed the Laplacian and they added this image to the Laplacian. Now they could clearly see the bones, but again, it also introduces a lot of noise. So because there is no, then what they do, they are computing Sobel of it. Okay. And then they are further even applying smoothing or Sobel by 5 by 5 smoothing. So this is what they got. Now you convert it into a mask. Now anything above a particular intensity value, you consider it as 255, otherwise it is 0. So you create a mask with 255. You create a mask on this smoothed Sobel, and this original and plus Laplacian, okay, whatever you are doing. So for that, now you apply this original plus Laplacian into smooth Sobel. So the rest you drop it and add it to your original image. So this mask is telling you what to retain from the Laplacian. Again, see, this is not the only way you could do it. Just try to get this idea that you could use, in fact, a further smoothed version of Sobel as a mask to get rid of noise in the Laplacian. Okay, these operations, when you think about it in bit more deep, you yourself could even figure out that in fact you could do it in different ways also. This is not the only way that that is possible. Okay, so don't pay attention too much, don't worry about it too much. For example, one thing I could immediately think about it is they are in fact using the original image twice. I could have come up with a slightly different workflow where I would add it only once. That's also is quite possible when I tried to analyze it, but that's okay. The take home message here is and then of course they are applying on this gamma transformation to further analyze it. The take home message here is, you could use on one side Laplacian, which captures everything. Okay, which is very yeah, captures everything, not worrying about the neighborhood. You could on the other hand use a different kind of thing, for example the Sobel edge detector, and further even if you want you could smooth it and then use it as a mask, and then a combination could perhaps give you in certain cases better detection. Okay, that's the basic take home message here. And then these combinations of whether you should add to the original image and how do you combine this, I myself could think of different possibilities here. Once you sit and try to analyze it, you would also come up with your own way of that. So that's not very, this is not the only unique way of doing it. There are different possibilities here, but the message, as I said, is you could use all these things. Then of course on this he is applying just 1 minute. So on top of it, you could apply then gamma correction also. You could see there they are using Laplacian, they are using Sobel edge detection, first order derivatives based one, and then the power transform. Okay, that's what is this example. Any questions?
So the order in which we apply these transformations, does that also affect the final output? Like if we, instead of applying the gamma transformation at the end, if we apply it in the beginning itself, uh,
it does affect here. See, because they are first of all trying to get the information of all these things were I think, for example, at the legs and other things, this information was not captured earlier. So this does affect, because first you are trying to highlight the edges and then you are trying to further improve it. Almost it is like saying almost that information is not there here. The edges are very bleak here. Okay, first you are increasing their intensities and then you are applying gamma transformation.
so gamma is used here to highlight the bone tissue only, right? Or is it just the surrounding tissue like of the legs and
gamma? If you remember, gamma correction, what it is going to do is a narrow band of intensities. You want to map them to a broad range of intensities. That's the basic idea. That's all it does. It does mapping from 1 to 1 only, but a small bandwidth of frequencies here could get on the y-axis mapped to a larger range of intensity values.
yes, sir.
Yeah, means at least we could say for sure that applying it here versus applying it gamma correction directly here versus here would definitely give different results, because the content itself is getting modified here. And then depending on the application, we need to see which one is better.
So doesn't the final image look more noisy than what we had originally? Like,
yeah, it is possible. So then you have to play with the parameters again. If see, one has to be very careful with particularly these medical images in all these operations. Although for the sake of having an example where all these things are involved, we are telling this example, but one has to be very careful when it comes to medical images applying these transformations. It could but at least they say here that the noise which is there in between is getting, because of the Sobel, got reduced, uh, but that's something debatable. Okay, I won't say for sure that this has definitely improved everywhere, but their point of contention here is they would like to see the bones clearly. The rest of the image they are not really worried as such, because the infection of the bones is what they wanted to analyze here. So in that case, I would say this is definitely improved. But again, I repeat that one has to be very careful while applying all these transformations and hoping that this is enhancing the image. One has to be careful that it has not introduced new noise, or it resulted in losing important information. That one has to be careful.
Sir?
Yeah.
Sir, in the second image, you said the original plus Laplacian into smooth Sobel.
Right,
So
right.
by doing into smooth Sobel, like what did you do exactly?
Yeah, I think 0 to 255 was a wrong statement. I think it is 0, 1 mask. So what they are doing is, once they have expanded the mask of the Sobel, if that is there in the Sobel region, then you retain that value. Otherwise, you drop that value. See, you have some Laplacian original, you got some
Yes,
Laplacian. Okay, on that result, what you are going to do, if it is there in an expanded version of your Sobel, you keep it. Otherwise, you drop it. That's essentially what they wanted to do.
Okay.
Again,
Like
there
if it
could
is
be some
equal
mistakes.
to,
Yeah. Sorry.
like in like programming, if it is equal to a pixel in the Sobel,
Correct. Exactly.
equal to 1 or else
So
0.
the mask is telling you is whether this is a potential candidate or not. So you will, if it is
Okay,
not there in smooth level, that's the first filtering it has to pass through. Otherwise, you drop it.
Okay, sir.
Yeah, there could be some mistakes whether they are actually adding it to the original or directly doing the Laplacian. I haven't worried about it to go in detail, but because the message is here a slightly different thing we are interested in here. Okay, that's also is possible. Maybe it is just the Laplacian that they are doing it and then adding it. That's also is possible. At least another way is also possible.
Okay, sir.
Yeah. Yeah. Any other questions?
Sir, what is smooth Sobel over here, sir?
Okay. Smoothed Sobel is here, for example, they are doing a 5 by 5, right? So what they could perhaps doing is it a assume that this is an averaging. So they have now 5 by 5 filter, which is 1 1 1 everywhere, 1 by 5. So they are probably, in fact, they could use a Sobel, and which is a larger size. Then that would also give you a similar result. But they are perhaps doing it just using 3 by 3 as their Sobel edge detection, and then again on top of it they are doing some smoothing, I guess. That's why this is not the only way of doing things. Actually, there are, I could myself see there are different combinations here. As you rightly pointed out, the smoothing also can become part of your Sobel, provided you are just increasing the size of your mask there for Sobel edge detection.
Okay, sir.
Yeah, good. Any other question here? Okay then, so we'll wrap it up here. Thanks for waiting for one more half an hour. It's good we are done with it. So from next class onwards, we would start image enhancements in the frequency domain. Along with it, we will be also building the basics that would be required. Okay, the building blocks that would be required for later understanding MR acquisition part also. So next class, I would start with a brief overview of means very really brief, maybe not more than half an hour for complex numbers, followed by we will see now one by one again continuous time Fourier transform to discrete Fourier transform. Okay, so I'll stop here. Let me stop the recording first. Okay.